Hello everyone and welcome. In this video we're going to compute the following limit. So the limit as n goes to infinity of n by 2 to the n times the integral from 0 to 1 of u of x divided by x to the n plus 1 minus x to the n dx, where u is a continuous function on the closed interval 0, 1. Okay, so let's get started. The idea here is to use Lebesgue Dominated Convergence Theorem. Okay, so we're going to denote by I sub n of u the integral. So n by 2 to the n times the integral from 0 to 1 of u of x over x to the n plus 1 minus x to the n dx. Okay, so what we want to do now is perform a change of variable by setting that x is equal to 1/2 plus y over 2n. And of course, n must be different from 0. Okay, so we're going to get new limits. So the lower limit is going to become negative n, and the upper limit will become n. So I sub n of u will then become 1/2 times the integral from negative n to n of u of 1/2 plus y over 2n divided by 1 plus y over n to the n plus 1 minus y over n to the n dy. Okay, so we want to write this as an integral over the real line. So it's going to be the integral from 1/2 times the integral from negative infinity to infinity of fn of x times gn of x dx, where fn is the original integrand and gn is simply the characteristic function of the interval negative n, meaning that it's the function that is 0 everywhere except on the interval negative n to n, where it's equal to 1. Okay, so now we want to gather all the ingredients in order to apply the dominated convergence theorem. Okay, so first of all, we are going to compute the pointwise limit of fn of x times gn of x. And because u is a continuous function, we can actually compute the limit of 1/2 of u of 1/2 plus x over n as n goes to infinity. And we're going to get exactly a u of 1/2. And 1 plus x over n to the n as n goes to infinity tends to e to the x. So we get u of 1/2 divided by e to the x plus e to the negative x. Now also notice that as n goes to infinity, the characteristic function will actually converge to the constant function that is equal to 1 everywhere on the real line. Okay, so now what we want to do is find an upper bound for the product fn of x times gn of x. Okay, so we're going to start by noticing that 1 plus x over n to the n plus 1 minus x over n to the n is equal to twice the sum as k goes from 0 to the floor of n by 2 times n choose 2k times x to the 2k divided by n to the 2k. Okay, so we see that on the right hand side, everything is actually positive because of the power 2k. Okay, so because everything is positive, this sum is always, as long as n is greater than or equal to 2, this sum is always greater than or equal to the first two terms of this sum. Okay, so it's greater than or equal to 2 times 1 plus n minus 1 over 2n times x squared. And because n minus 1 over n is greater than or equal to 1/2 for n greater than or equal to 2, we get that the left-hand side is actually greater than or equal to 2 times 1 plus x squared over 4. Okay. Now, because 1 plus x to the n, 1 plus x by n to the n plus 1 minus x by n to the n is actually in the denominator, when we divide by that quantity on the left-hand side, the inequality is going to be reversed. We can deduce that the absolute value of fn of x times gn of x is actually less than or equal to m divided by 2 times 1 plus x squared over 4, where m is simply the maximum of the absolute value of u for x between 0 and 1. And of course, we can simplify this as 2m divided by 4 plus x squared. And we clearly see that this function is integrable from negative infinity to infinity. We're going to get some arctangents. Okay, so now we have all the ingredients of our Lebesgue Dominated Convergence Theorem. So every product fn times gn is integrable because we're actually multiplying by some kind of cutoff function. And then the pointwise limit converges to a function that is integrable. Okay, so we can apply the Lebesgue Dominated Convergence Theorem, and we're going to have that the limit of I sub n of u is equal to, now we just apply the dominated convergence theorem, the limit that is outside of the integral goes inside the integral. So now we just need to take the integral of the limit, but this limit is known, the pointwise limit is known. It's u of 1/2 divided by e to the x plus e to the negative x. Okay, now notice that we have an even integrand. Because we have an even integrand, we can simply integrate from 0 to infinity and then multiply the result by 2. Also, u of 1/2 is just a constant, so we can take it outside of the integral. So, taking outside of the integral the constant u of 1/2 and multiplying by 2, we get u of 1/2 times the integral from 0 to infinity of 1 over e to the x plus e to the negative x dx. Now we want to multiply the top and bottom by e to the negative x. Okay, so we're going to get the following, and then we're going to perform a change of variable. So this is our second change of variable. So we want to set that t is equal to e to the negative x. So we're going to get u of 1/2 times integral from 1 to 0 of negative 1 over 1 plus t squared dt. Now we can change the order for integration. So the upper limit will become the lower limit and vice versa. That's going to bring out a minus sign. That's going to cancel out with the minus sign in front of the integrand. So we're going to get that the limit is equal to u of 1/2 times the integral from 0 to 1 of 1 over 1 plus t squared dt. An antiderivative of 1 over 1 plus t squared is simply arctangent of t. Okay, so we're going to evaluate it between 0 and 1. So we're going to get arctangent of 1 minus arctangent of 0. Arctangent of 0 is 0, and arctangent of 1 is simply pi of 4. So we get that the limit of n by 2 to the n times the integral of from 0 to 1 of u of x over x to the n plus 1 minus x to the n dx is equal to pi over 4 times u of 1/2. Okay, thank you for watching. Consider subscribing if you like these kind of videos, and I'll see you next time. Bye.